Okay, so in our, I think about second to last video, maybe third to last, but I think second to last video on climate change in Physics for Future Leaders, is we're going to look at some of the evidence of human influence on climate. And we've talked a lot about drivers of climate change, all the different things that feed into forming Earth's climate. And we've talked about the root cause of climate change, right, the greenhouse effect. And we've talked about these drivers of climate, but none of them, as you'll recall, that we've discussed, and none of them in general, can explain this recent increase in global temperatures. And the answer to the basic question of what is causing this recent run-up in global average temperatures is we humans. And some of the starkest evidence, though there's certainly lots more beyond what we'll go over in this short video, some of the starkest evidence is what we're looking at right here in the graph on the left. So if we look at this briefly, let's break it down. So carbon dioxide and oxygen in the atmosphere. So we have two y-axes. So over here on the left, we've got carbon dioxide in parts per million. Okay, so 1 molecule of carbon dioxide in a million molecules of atmosphere. So 400 parts per million is what we're looking at here on the top right, okay? And you'll notice that the blue line is the one corresponding to, hold on a second, let me grab my pen here. So the blue line is the thing that is tracking carbon dioxide. And you can see from in the data set that we've got here, we're tracking from just after 1990 until about 2014, and you can see a steady increase, pretty smooth with seasonal oscillations, in the carbon dioxide content of the atmosphere. And at the same time, you see here in the red line the ratio of oxygen to nitrogen in the atmosphere trending down. Okay? So why would this be? Why is this stark evidence? Well, the thing to remember here is that to get carbon dioxide, you can get it from a fair number of different sources, right? So historically, you've got things like rock weathering. Various rock formations have a lot of carbon bound up in them, and so they can break down and turn into carbon dioxide. And so historically, like millions of years ago, about 3.5 million years ago, when we were last at about 400 parts per million CO2, so sort of approximately where we are now here on the graph. That was about 3.5 million years ago, and that wasn't due to humans being around. Right, that was due to natural effects, volcanism, that was due to rock weathering, that was due to all kinds of other natural processes that can also affect the carbon dioxide in the atmosphere. Okay, so the reason this graph is stark evidence that we are the ones causing this is that combustion requires oxygen to produce the carbon dioxide and water vapor and things like that come out of combustion processes. So whenever we burn coal or burn natural gas or something along those lines, we create carbon dioxide, and we create that by combining energy and O2, right, atmospheric oxygen. So we would expect that if we want to see evidence that us burning carbon-containing fuels is causing the increase in carbon dioxide, specifically that process, that combustion, then we would expect to see a decrease in the oxygen in the atmosphere, and that's exactly what we see. Okay? So there's that. Now, a couple of things here. We're not going to wipe out all the oxygen we need to breathe, right? These are tiny changes, so per meg is a part per million change in the ratio of oxygen to nitrogen. So it's not that we're going to asphyxiate ourselves by burning fossil fuels, but we are using up some tiny amount of atmospheric oxygen, and it shows this very clear relationship between the increase in carbon dioxide and the decrease in oxygen as we combust materials to use up oxygen and create carbon dioxide. Now, the other graph I'd like to show you, and sort of further evidence for knowing that it's the CO2 in our fuels that is causing this increase in carbon dioxide and thus an increase in global average temperatures, is this graph, courtesy of an Australian climate science outfit, the CSIRO. And if you look at this graph, let's see what it's telling us. Okay, so concentration, isotopic composition of atmospheric carbon dioxide. All right, so over here on the left, kind of like in the left-hand graph, we've got parts per million atmospheric CO2 concentration. And they've smoothed the graph so that you're not seeing all of the seasonal variations, and they're doing it over a much longer period of time. So they're getting this from proxy data, at least until you get up to sort of modern day up here. Okay. So the red curve here is the CO2. So low, 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 little dip here, and then a big increase in modern day. Okay, so that's something we already know about. Okay, now the thing that's new in this graph, and that what they're pointing out here, is the black curve, which is the ratio of carbon-13, the isotope carbon-13, to carbon-12 in that carbon dioxide. Okay, so you see that it falls off a cliff, relatively speaking. Okay, again, we're talking about sort of per mil or per meg. Sorry, per mil changes. They're similar, but off by a factor of 1,000. In any case, what this is telling us is that the ratio of carbon-13 to carbon-12 is going down. And it's a reasonable question to ask, why does that tell us that it's fuels being combusted that are causing this CO2 rise? Well, when plants fix carbon, right, they grow, they do photosynthesis, and they take carbon from the air, in the form of carbon dioxide, and they respirate it, and out comes CO2, or rather O2, and they fix that carbon in their structure, right? They use it to grow. But the process by which they do that preferentially uses lower weight isotopes, lower mass isotopes. So they much prefer the much more common carbon-12 than carbon-13 or any of its other heavier isotopes. Okay? So when we burn trees or fossilized trees, we are putting back into the atmosphere a bunch of carbon that has a much higher proportion of carbon-12 than we would have just sort of normally in the atmosphere. And so when we see this big cratering of the ratio of carbon-13 to carbon-12, well, what that's telling us is that that's exactly what's happening. We're combusting wood and fossilized wood, in the case of carbon and things like the hydrocarbons, fossil fuels, quote unquote, and that's driving up the amount of carbon-12, right, because that's the stuff that they fix preferentially in their structure, and then they die, and then it becomes part of natural gas and coal and all of that kind of thing, okay? But we're spewing a whole bunch of that carbon-12 back into the atmosphere, so the denominator of the ratio between carbon-13 and carbon-12, the denominator there gets bigger, because that's the carbon-12, and that means the ratio of carbon-13 to carbon-12 gets smaller and smaller and smaller, as this graph shows, okay? If it was being caused by some other natural process, we wouldn't expect this big drop in that ratio. We'd expect the ratio to more or less mirror what was in the atmosphere already, and for this curve to, instead of going down, perhaps staying more or less constant. Okay? So, two bits of strong evidence for the influence of humans on the current run-up in CO2 in our atmosphere, and thus the increase in average global temperatures. When we come back next time, we'll have probably a little bit of a longer video on the effects of climate change already observed, and also the expected effects of climate change to illustrate why this is such a problem, both for human existence and our way of life, and also as a conundrum for policymakers to pull the right levers to get us away from this rapid increase in temperature. So, thank you for listening, and I will see you next time.